Hello, I'm Markus Wenk. Thank you for your interest and time in watching this short video. It's my distinct pleasure to have this opportunity to introduce you our program and passion for research and graduate education. My team and I firmly believe that better technology opens new opportunities. In our case, this relates to detection, identification and quantification of molecules that were hitherto difficult to follow. Over the past decade and a half, we have been developing and applying new technology for the study of biological molecules. The basis of our platforms are chromatography and mass spectrometry. We use such advanced analytical approaches to measure, qualitatively and quantitatively, metabolites from various sources. One type of metabolite that has been of keen interest to us are so-called lipids. These are small molecular weight compounds found throughout all kingdoms of life. Now, please join me to the whiteboard for a short excursion. Oils, for example, are lipids and are quasi-entirely composed of hydrocarbon chemistries. This is a pretty common way to represent hydrocarbons. C for carbon and in black, and H for hydrogen, typically white. Linear strings of such carbon-carbon chains are the essential ingredients in petrochemical fuels, though they are typically a bit longer than what is shown here. During combustion, such reduced forms of carbon are reacted with oxygen to generate energy in the form of heat or light, which, when engineered appropriately in an engine, can be utilized for motive forces or to generate electricity. But of course, you know all of these old school technologies. Well, nature is using the same basic chemistry to generate biological or biochemical energy. In that case, hydrocarbons or fatty acids in biochemical terminology are converted to high energy intermediates such as ATP instead of heat and light. But in addition to that, nature has built many more functions into the otherwise dull black hydrocarbon landscape. These decorations have certain basic characteristics. First, they're made up not only of carbon, but also of other elements, such as oxygen in red, phosphorus in yellow, sometimes nitrogen here in green, and maybe occasionally sulfur in purple. This introduces unique chemical properties distinct from carbon-carbon and carbon-hydrogen bonds. Second, quite often, these features are grouped on one end of the hydrocarbon mainframe. This adds handedness, which relates to profound properties described best in biophysical terms, of which surface activity is a major one. This property, for example, dictates assembly of biological lipids into lipid-lipid aggregates, such as bilayer membranes or lipoprotein particles. Third, and possibly most intriguing and wide open for future discoveries, the colored bits of lipids are metabolically and functionally linked into networks. We know the principal wiring of these networks, but many metabolic reactions, transport chains, and most importantly, the regulation at system scale remain poorly understood. Chromatography for separation and mass spectrometry for detection are ideally suited to address the complexity of biological lipids in mixtures. And this is precisely what we are pursuing at the Singapore Lipidomics Incubator. A green letter S, pink L, downward I, green N, and red G are embedded into our imaginary and iconic lipid structure. Now let's see where you can find us. Sling is a research program at the Life Sciences Institute. Our core team of approximately 25 students and staff works closely with about 15 visiting scientists as well as colleagues from other LSI programs. We're located at the Center for Life Sciences, which shapes the interface between NUS Science, the School of Public Health, the School of Medicine, as well as the National University Hospital, and thus ideally positioned for interdisciplinary research and education. And indeed, collaborative teams composed of members from these different faculties and schools drive many of our current projects. So how does all of this fit into the local and international research landscape? Well, it turns out that aberrant lipid metabolism is correlated with major human diseases. These include inflammation, cancers, metabolic and cardiovascular disease. And thus, our capabilities and contributions in analytical sciences are met with rapidly increasing interest by our colleagues in this biomedical ecosystem and beyond. We're now able to measure with high definition circulating metabolites in human blood. This helps in basic and clinical research, advancing our understanding of human health and onset of disease. We embrace partnership and are engaged in large-scale programs with industry and national-scale endeavors. The NUS Adjuvant Hub for Translation and Capture, for example, is positioned as a premier global one-stop hub for research and translation to clinical testing through biochemical innovation and techniques. We're currently investing a lot of R&D efforts into high-throughput mass spectrometry. This will allow us in the near future to align metabolite maps with genomic maps. The latter come from established and newly formed precision medicine programs at NUS and in Singapore. Sling is also an integral component of SIGMAS, a national consortium to provide comprehensive solutions for mass spectrometry applications and technology development. Finally, Sling organizes well-recognized international workshops and symposia, training courses, and a new thematic online forum. These go under the acronyms of ISLS, IC Lipid, and 7 to 11 at Sling. We work with our partners in Asia Pacific and the rest of the world on standardization and harmonization. Collectively, these community efforts will help tremendously in translation of mass spectrometry-based approaches to clinical applications. Thus, to conclude, we are a global magnet for collaborative parties in lipidomic research and education. Thank you very much once again for your attention.